Today, we're diving into what might be the single most ambitious project in all of human history, the race to build artificial general intelligence, or AGI. And look, we're not just talking about a smarter chatbot here. This is the quest to create an artificial mind that can reason, create, and solve problems just as well as we can, or maybe even better.
So, what exactly is AGI? Well, people in the field call it the Holy Grail for a reason. Imagine an AI that doesn't just master one thing, like playing chess or writing an email. Imagine an AI with the flexibility to learn and tackle any intellectual task a human can. It's not about being a specialist, it's about having the general cognitive ability to be good at, well, pretty much everything.
Okay, so that's the goal. But the billion-dollar question, and I mean that literally, is how in the world do we get there? It turns out the top AI labs on the planet are placing massive bets on some wildly different strategies to be the first to crack the code.
All right, let's start with the current champion, the approach that's dominating all the headlines. This is the bigger is better bet, also known as the scaling hypothesis. The core idea here, which is championed by giants like OpenAI and Google, is almost shockingly simple. We don't need some clever new breakthrough algorithm. We just need more scale. A lot more. You take a massive model, you feed it basically the entire internet, and you throw an absolutely insane amount of computing power at it. And here's where the magic happens. You get what are called emergent behaviors. The AI starts doing things it was never explicitly taught, like writing code or explaining a joke. It just learns. But, and this is a huge but, there's a major pushback against this idea. Critics have this fantastic term for it. They say these models are just stochastic parrots. They're arguing that no matter how big these things get, they aren't actually understanding anything. They're just getting incredibly good at predicting the next word in a sequence. So the big question is, are we building a true intelligence, or are we just building the world's most sophisticated autocomplete? And that very criticism, that fear of building a brilliant parrot, has fueled a whole host of challenger theories. These are the folks who argue that brute force isn't enough. We need to build an AI that's smarter, not just bigger. First up for the challengers is something called neurosymbolic AI. The best way to think about this is like building a hybrid brain. You take the creative, pattern-matching neural net, that's your right brain. Then you combine it with old-school, rule-based, symbolic AI, your logical, mathematical left brain. The goal is to get the best of both worlds, an AI that has intuition but can also reason logically and check its own work. Our next challenger is a really cool concept called world models. This is championed by AI pioneer Yann LeCun at Meta, and he basically argues that predicting words is a dead end. To get to true intelligence, he says, an AI needs to build an internal mental model of how the world actually works. It needs common sense. So how does that even work? Well, instead of feeding the AI text, you have it observe the world, say by watching videos. And here's the crucial part. It's not trying to predict the next pixel in the frame. No, it's trying to learn to predict what happens next on an abstract level. It's learning cause and effect. Over time, it builds its own internal simulation of physics and reality, which it can then use to plan and reason. Now, this next idea takes that concept a giant leap further. It's called embodied AI, and the theory is radical but simple. A brain in a jar will never be truly intelligent. For an AI to actually understand the world, it needs a body. It has to physically interact with things to ground its knowledge in reality. And here's a perfect way to picture the difference. For a large language model, the word apple is just a symbol connected to other symbols like red, fruit, and pie. It's all abstract data. But for a robot with a hand, an apple is something it can see, touch, feel the weight of, learn the texture of. One knows about an apple. The other knows what an apple is through direct experience. So every path we've looked at so far is about trying to build an intelligence from scratch. But what if there's another way? This brings us to our final contender, the wild card, the long shot, which looks directly to biology for the blueprint. This is called whole brain emulation, and yeah, it's straight out of a science fiction novel. The plan is to literally reverse engineer the human brain. The idea is if we could scan every single neuron and every single synapse, the brain's complete wiring diagram, and then perfectly simulate that structure on a powerful enough computer, the software of the mind, consciousness and all, should just emerge. Okay, so we've got the frontrunner, the challengers, and the wild card. We have all these incredible competing ideas. So how does this all stack up? Who actually has a shot at winning this race? This chart really lays out the state of play. You've got the scaling approach, the more is more philosophy, but it's hitting some serious walls with data shortages and insane energy costs. Then there's neurosymbolic AI, which is a great idea, but actually getting the two different systems to work together smoothly is proving to be incredibly difficult. World models promise common sense, but training them is a nightmare of complexity. And finally, you have embodied AI, which is a fantastic theory, but it's held back by the simple fact that robotics hardware is still pretty slow and clumsy. Which brings us to the final massive question. The race is on. The stakes are unbelievably high. Is one of these paths going to be the silver bullet, the single breakthrough that gets us to AGI? Or is it more likely that the real winner won't be a single approach, but some kind of hybrid, a fusion of all these ideas? That is the question that will define the future of intelligence itself.